Hello, my name's Jennifer Duncan. I'm a PhD student at the University of Birmingham, and my research is in nonlinear Brascamp Lieb inequalities. But before I talk about them, I just want to talk a little bit about restriction, specifically multilinear restriction. So this inequality is just it's an LP bound on a product of extension operators associated to some hypersurfaces Sj, applied to some L2 functions Fj. And the picture here is one that we should be familiar with by now. We're really we're trying to bound a product of sums of modulated indicator functions. Now, it's quite reasonable to then say, well, if we want to understand this, we should really understand the non-oscillatory version of this, i.e., where these indicator functions are not modulated. So this is just the K inequality. So the geometry is the same, essentially, but the inequality is quite different. Rather than having hypersurfaces, we've got collections of tubes. If we want to understand the Kakea inequality, the multilinear Kakea inequality, we should really understand it in the simplest geometric setting. And this is where the tubes in each family are all parallel to one another. And this is what we refer to as the Loomis-Whitney case. We can express it in this nice functional form because we can do this density argument where we express tubes as preimages of balls. Now, the great thing about the multilinear restriction problem is that it's easier than the linear one. We actually are able to prove results up to the endpoint under pretty simple transversality hypotheses. So suppose that you have some compact hypersurfaces, S1 to Sn, such that if you take any configuration of points, then the determinant of the matrix that you make by putting together all of their normals is always greater than some number nu. Then you have your non-endpoint restriction inequality up to the endpoint. And we do have to tolerate a certain polynomial loss, but this is very good. Now we know even more in the Kakea case. So suppose a similar thing, rather than configurations of normals of points, we have these E of Tj's are directions of tubes. And suppose that these directions are always transversal. Then we have this inequality, and this does hold at the endpoint. And notice that we have this nu arises explicitly in this inequality, and it's the same constant that you have in the Loomis-Whitney case as you would expect. I guess the point I'm trying to make is that the Loomis-Whitney is the fundamental geometric thing that's going on in restriction and in Kakea. So you really need to understand that in order to understand either of those two problems. Now, you can consider more general setups where your Sj isn't just a hypersurface, it could just be just a lower dimensional submanifold. Now, the corresponding Kakea problem is where the slabs have the codimension of these submanifolds, right? Because that's what the wave packets look like. And then you can ask, okay, so then, so what's the Loomis-Whitney? What happens to Loomis-Whitney? Well, then rather than just projecting onto the orthogonal complement of the direction of the tube, you're just projecting onto an nj dimensional subspace. And so I guess that this is what I'm going to be talking about today, because this is Brascamp Lieb. And so I suppose the argument I'm making right here is that if you want to understand multilinear restriction in Kakea in general dimensions, you need to understand the fundamental geometric phenomenon going on, which is Brascamp Lieb. So the Brascamp Lieb inequalities are this: you have say you have a collection of m linear surjections, each with a corresponding exponent pj. We call this pair of tuples of the LJs and of the PJs a Brascamp Lieb datum. The associated inequality is this, where we precompose all these FJs with the LJs. These FJs live on these lower dimensional spaces RnJ, and then we integrate them back in Rn. I should just say, in the context of Brascamp Lieb, all of the FJs I'm going to be considering are positive. It's all positive. So just some useful terminology is the Brascamp Lieb functional, where we take the left-hand side, divide it through by the right-hand side. The Brascamp Lieb constant, which is just the supremum of the Brascamp Lieb functional, and it's the best constant for the Brascamp Lieb inequality. Now, you can ask some interesting questions about the Brascamp Lieb constant. This being, is it continuous in L? And on the set on which it's finite, this is true. But you can also ask the question of is it differentiable? Is it twice differentiable? And the answer is no. And you can construct some interesting counterexamples to this. So there's a scaling condition that arises where if you want this Brascamp Lieb constant to be finite, you need for the Brascamp Lieb functional to be stable under certain rescalings of the FJ, and this just gives you this this fairly trivial scaling condition, under which we then have this broad class of invariances that I'd like for you to bear in mind. So I guess a key thing is that that the Brascamp Lieb functional is constant under L1 rescalings, which is important. So take Lieb's theorem. This is kind of a fundamental thing in Brascamp Lieb theory, which is that you only need to test on Gaussians, which I mean by just inputs of the form just exponential of minus and in a product. So this AJ is just a general symmetric positive definite matrix. So the Bennett-Carbury-Tau theorem, as I call it, is a theorem that gives you necessary and sufficient conditions, not just for the finiteness of the Brascamp Lieb inequality, but also for extremizability and unique extremizability. So it's very powerful. I'm just going to go over some basic definitions to begin with. So suppose that LP is a Brascamp Lieb datum, such that you have the scaling condition, and also that this, this is sort of a slightly weakened version of the scaling condition, but holds on all subspaces V and Rn, and we call such a datum feasible. Now, if you suppose the slightly stronger thing that actually that 2 holds strictly for all proper non-trivial subspaces, then we say that this datum is simple. We kind of view simple data as being like a fundamental building block for linear Brascamp Lieb inequalities, because if your data is non-simple, then there exists a subspace for which the scaling condition holds, and then you have and then your Brascamp Lieb data restricts to that subspace, and kind of it makes sense as an inequality there, and so your datum decomposes in this sense. So the theorem is this: if your datum is feasible, then then the associated Brascamp Lieb constant is finite, and vice versa. Moreover, the inequality associated with LP is uniquely extremizable by a Gaussian, if and only if the datum LP is simple. And there's another thing, which is extremizable by a Gaussian if and only if LP is semi-simple. I'm not going to go into too much detail over what that means. Suffice to say that LP is in some sense equivalent to a direct sum of simple data, which as I say, I'm not going to define that, but just to kind of give you a flavour of this extremizability property. And I think it's important because lots of the really important examples of Brascamp Lieb inequalities, these being Hölder's inequality, Loomis-Whitney, Young's inequality, these are, well, Young's inequality, except for in certain cases, is mostly semi-simple. Now, just to kind of pin down the point I was making earlier, suppose that you have a collection of submanifolds, not hypersurfaces, just submanifolds, such that this Brascamp Lieb constant associated with the projections onto the tangent spaces of the submanifolds holds with finite constant, then this integral, this multilinear extension inequality, this holds, and not just with just the same exponent of 1 over m minus 1, but with these more general configurations of exponents. And it does say these have to be small submanifolds, i.e. you have to take them sufficiently small. But I should imagine that this jacks up to just the case of compact submanifolds. I would imagine, but I don't know how exactly you'd prove that. So what if we allow LJ to have some nonlinearity? Now this is something that kind of commonly crops up in lots of different situations. So Carl, Leeb and Loss, they stumbled across Brascamp Lieb inequalities by looking at certain entropy related quantities and seeing that, well, this was actually just sort of a Loomis-Whitney type of functional, but where you're integrating not rather than over Euclidean space, you're integrating over a sphere. And also in a paper of Bejanaro, Hare and Tataru, where they are they ended up thinking about convolutions of densities supported on surfaces in R3 from looking at these XSB spaces. And then in Lie theory, Cowling, Martini, Muller and Parset end up referring to this forthcoming local nonlinear Brascamp Lieb inequality when looking at Young's inequality on the Lie group and seeing how that approaches the behavior of the Euclidean Young's inequality as you restrict closer and closer to the identity. But I also like to just kind of bring this back to oscillatory integrals for a bit. So if you consider this very generic oscillatory integral operator, no cutoff or anything, and you just suppose, well, what if my phase was linear in one of the two variables? Well, then, if it's linear in the second one, then you have an extension operator. If it's linear in the first, then you have the Fourier transform of f composed with some map B. Potentially, it's a submersion or something. And so you can kind of think of Fourier extension and nonlinear Brascamp Lieb as living on two opposite sides of a broad class of multilinear oscillatory integral estimates. So this is a picture that I kind of like. So this is a very important inequality, very general. And essentially, it answers the question of, if I have a collection of nonlinear Brascamp Lieb data, if I have some submersions Bj, that if I take the derivative at a certain point, it looks like a linear datum for which the inequality holds, i.e. if it looks like a feasible datum, then is there a neighbourhood around that point on which the associated nonlinear inequality holds? And the answer is yes. Moreover, the best constant in that nonlinear inequality is going to get closer and closer to the linear constant as the size of that domain of integration goes to 0. So yeah, this is the inequality. So yeah, so something to note is that this doesn't quantify the relationship between the size of the domain of integration U and the error, this epsilon here. But we do address that later in an improvement of this inequality that you can establish. So I want to talk about the proof of the local nonlinear Brascamp Lieb inequality. But in order to get an intuition for that, I'd quite like to just first of all just talk about Ball's inequality. So this is quite nice. Hopefully you can follow along. Now we start off by just saying, okay, well, let's just take the linear Brascamp Lieb inequality. Just take two left-hand sides for different inputs, fj and gj. And, well, we can just write this as just an integral of a convolution. Just harmless. Right? Now we can then use the linearity of the Lj to separate out the x and the y. And then we observe that, well, we have a Brascamp Lieb form in the inner integral, although the function has some dependence on x. You can think of this fxj as kind of like if gj is very highly localized to near 0, then this is kind of like a localized version of fj. But we can apply just the definition of the Brascamp Lieb functional here, and then take a supremum. And when we're left with an integral of fxj, which you can pretty easily see is just the convolution of fj with gj, then evaluated at Lj of x. And so what we've arrived at is Ball's inequality, which is that the product of the Brascamp Lieb functionals evaluated at f and g is bounded above by the supremum of these localized versions of f and the Brascamp Lieb functional evaluated at the convolution of f and g. So you can ask the question, okay, well, why is this significant? Well, suppose that G is a Gaussian extremizer. Then we can divide through in two different ways. One is that we can bound the Brascamp Lieb functional of f above by the supremum of localized versions of f, or we can bound it above by the convolution of f with g. Now, this tells you some interesting things. So first of all, suppose that f and g are both extremizers. Then what this shows is that the family of extremizers is closed under convolution. Moreover, if you take, say, an extremizer f, you convolve it with itself, right? And you just do this iteratively, then by the central limit theorem, it's going to converge to a Gaussian, which implies that if you have an extremizer for your Brascamp Lieb inequality, then you have to have a Gaussian extremizer by this iterative procedure. But also, I say here, this is heat flow monotonicity. If G is a Gaussian extremizer, then all of its L1 rescalings are also Gaussian extremizers. So I may as well have written G sub T there rather than just T. So this really is a heat flow monotonicity statement. Okay, so what if my Brascamp Lieb data is not extremizable? Well, there is a perturbation of this. So if you have a delta-near extremizer, then still you can say something. You can this localization thing still works, but you accept an error, and likewise with your monotonicity statement, you have a near monotonicity statement. Now, do similar statements to these, like both in the exact and the delta-near case, hold in the nonlinear case? And well, for the former, yes, they do. But just before we talk about that, we're just going to talk about the strategy for proving the local case, proving the local argument, which amounts to establishing a nonlinear version of 1 by running a ball type argument like we saw before. And at the end of it, we're gonna get something like this. If we integrate around a certain ball, then accepting a certain amount of error, because in general we're not going to have an exact extremizer, we're going to have a near extremizer, a supremum over smaller balls, at scale delta to the alpha, where alpha is, say, is greater than 1, of these smaller balls. And then the idea is that we can iterate this, right? We can keep on going down, down, down to arbitrarily fine scales. Now, suppose that suppose that fj was constant at scale, I don't know, delta to the alpha to the 1000. Then at that scale, fj would not be able to detect the difference between bj and its affine approximation, which means that we can then harmlessly switch out the bj of x for the affine approximation, and then apply the linear inequality. So this is kind of like the general idea of this proof, but most of the hard work goes into establishing this kind of recursive inequality. And part of the difficulty of that is that you need a delta near extremizer in order for this to work. And moreover, your delta near extremizer needs to be, it can't become arbitrarily long and thin as delta goes to 0. It has to be its eccentricity has to be polynomially well controlled as delta goes to 0. So and they refer to this as an effective Lieb's theorem. Effective in the sense that it's quantitative. And we're going to talk a little bit about that later, and certain improvements that you have to make for the theorem that I'm going to talk about later. Now, exact monotonicity properties hold for nonlinear Brascamp Lieb inequalities in certain special cases. On the sphere, as was proved by Carl, Leeb, and Loss, and in compact homogeneous spaces by Ramati. So the proofs use the geometry to run just certain direct calculus methods, just differentiating with respect to time and just showing that this derivative is greater than 0. But it's reasonable to ask, okay, is there a more universal statement? Is there a statement that holds that, for say, for near monotonicity? And the answer is yes. So suppose that you have some C2 submersions such that your BJ has well-controlled derivative, and that the Brascamp Lieb constant is uniformly bounded. Then you have a family of truncated heat kernels, one for each x, and an epsilon greater than 0, such that for tau sufficiently small, you have a near heat flow monotonicity statement with a polynomial error in tau. And this Gx tau j satisfies some quite nice properties. So, and this is the effective Lieb's theorem that I'm going to be talking about. So, Gx tau j takes this form, which kind of looks like an x-dependent mollified Gaussian. But notice that there is also a tau dependence in the positive definite matrix A. And we need this because we need for our G x tau j to get closer to being a genuine extremisor for the datum dBxj for the derivative data as tau goes to 0, and moreover it needs to be polynomial. But also we need for this matrix A x tau j to be nice and well controlled, and so this is a third property. Now, Bennett, Bez, Brascamp, Flock and Cowling, they essentially proved this theorem, but the only difference is that this this Sobolev bound, number 3, they only prove an L infinity bound. Right, they don't prove any regularity or anything. But I had to improve this in order to be able to apply it to my theorem. And the way that you get the Sobolev bound is just there's just a certain local averaging procedure that you need to do that actually exploits the linear Ball's inequality in order to so that when you average, the average that you're left with is still a delta near, or rather a tau to the alpha near extremisor. That's essentially it. Now, the inequality is a global one, and so it's kind of reasonable to suggest that, okay, well, what if this should hold in just more general geometric context? So if you suppose that M are Riemannian manifolds, and there is also this technical issue of they have to have bounded geometry, which just means that the Riemannian curvature is uniformly, the Riemannian curvature tensor is uniformly bounded above. Then, right, we have this heat semigroup. So kind of like our Gaussian's G x tau j, or rather it's like convolution with the Gaussian's G x tau j. But obviously, if you're on a manifold, then convolution doesn't make sense except locally. So some corollaries. So we can use this this heat flow near monotonicity statement to improve the local nonlinear Brascamp Lieb inequality. And the idea is this just that we flow up to a point where the FJs no longer, are very nice and locally constant, at which point we just we then perturb globally to the associated linear inequality. So that's the idea behind that. And we also prove a stability statement, which is just that if you have if you have two nonlinear Brascamp Lieb inequalities, and you know that the first one has well controlled submersions that satisfy the conditions of our nonlinear Ball inequality, and the second one is just holds with finite constant. Then if they're a finite distance away from one another, then we have that the first one also has to hold with finite constant. So as far as I know, stability statements of this type don't exist yet, and also most of the global nonlinear Brascamp Lieb inequalities, these aren't stable under perturbation, or at least the statements aren't stable under small perturbations. So this does give you actually quite a lot of new inequalities. So I guess that's all I wanted to say. Thank you very much for listening.